Today, we tackle a problem that asks us to count specific elements within an array. The challenge lies in efficiently determining a particular relationship between numbers. Can you find a way to count these elements without redundant checks? Given an integer array, we need to count how many elements x have x plus 1 also present in the array. If there are duplicates, each instance of x should be counted if its successor exists. The core task is to check for the immediate successor for every element in the input. A straightforward but inefficient approach is to iterate through the array for each element x. For every x, we then run another nested loop through the entire array to see if x plus 1 exists. If it does, we increment our count. This involves a lot of repeated searching. Each check for x plus 1 requires potentially scanning the whole array again. This leads to a quadratic time complexity, O of n squared, because of the nested loops. Space complexity is constant, O of 1, as we use no extra data structures. The key insight to optimize this is to use a data structure that allows for very fast lookups. Since we frequently need to check if a number x plus 1 exists, a hash set is ideal. First, we populate a hash set with all unique elements from the input array. This takes a single pass. Then, we iterate through the original array one more time. For each element x, we simply check if x plus 1 is present in our hash set. Because hash set lookups are typically constant time on average, this significantly speeds up the process. If x plus 1 is found, we increment our total count. This separates the population of unique elements from the checking logic, making it much more efficient. Let's trace this with the example array 1, 2, 3. First, we'll populate our hash set. It will contain 1, 2, and 3. Now we iterate through the original array. For the first element 1, we check if 1 plus 1, which is 2, is in the hash set. Yes, it is. So our count becomes 1. Next, for the element 2, we check if 2 plus 1, which is 3, is in the hash set. Yes, it is. Our count becomes 2. Finally, for the element 3, we check if 3 plus 1, which is 4, is in the hash set. 4 is not present, so our count remains 2. The loop finishes. The final count is 2. This is correct because both 1 and 2 have their respective successors, 2 and 3, present in the original array. 3 does not have 4, so it's not counted. You'll spot this pattern when you need to frequently check for the existence of specific values or their derivatives within a collection. If your brute force involves repeated linear searches, consider if a hash-based structure can provide average constant time lookups to optimize. The time complexity for this optimized solution is O of n. As we iterate through the array twice and hash set operations are average constant time. The space complexity is also O of n, due to storing elements in the hash set. Try the next problem that involves frequency counting, same pattern. If this explanation helped, please like and subscribe for more efficient DSA solutions.